Now, in doing this, you saw me use several little simple properties of radicals. I'm going to go ahead and line those out. You'll be able to see them here, where it says properties of radicals. Excuse me for just a second. I thought I was going to need to do something. Never mind. My bad. Okay. First one, if you're raising a base to the exponent that is equal to the root, the root index and the exponent equal each other, they cancel each other out, and you're left with just a base. If they do not equal each other, such as this case, then you write it as the base to the exponent over the root index. This is the opposite of what we did earlier, but it shows you that you can go both ways. Just because you are accustomed to writing x to the b over a here, I'm writing it upside down on purpose, then that means it's a to the x to the b, right? Or you can write it a x b. Well, if you have this, you can just as easily write it as x to the b over a. Remember what we did up here where we were simplifying the fourth root and the sixth exponent. Rewrite it as a fraction, then you can reduce the fraction, and when you come back, it's probably going to be a lot more manageable. Then we have this idea right here that you saw me use in the first one. If I have a square root of a times b, that is the same as the square root of a times the square root of b. I did that just up here. Let's see. When I did the square root of 20, I separated square root of 4 times 5, then I did the square root of 4 times the square root of 5, and I was able to take the square root of 4, but not take a square root of 5, and I reduced it down. Similarly, when we had a radical in the denominator, I used this property, which is the same thing as the previous one. If you're dividing a divided by b under the radical, that's the same as the radical of a divided by the radical of b. Basically, you can separate the numbers under the radical. And the last one, this one isn't one you're going to run into very often, but it is useful to know. If you're taking the radical of your base, let's say the b is the root index of this radical of x, okay? And then you need to take another radical of it with a different number a. It doesn't matter what order you take that radical. You can do a and b, or you can do b and then a, like you do in the second example here. Or you can just multiply a times b and do one radical over the x, like this one right here. These are properties that you can use to manipulate radicals. And here are some examples of them. All right. Now, in class, I did a couple of these trying to help everybody out. So I'm just going to start by doing the first one on each of these. If we look at 3a, okay, we have 252 under the radical. 252, that is not a perfect square. I can tell you that personally. You can try and take the square root of it. You'll get a number with a decimal that keeps going. But we can try factoring it out. Now, I personally, when I see it's an even number, just out of habit, I try a 4. I want to see if it works. Sometimes it does, sometimes it doesn't. But if I pull a 4 out, I know that's a perfect square that I just pulled out. So let's give it a try. If we divide 252 by 4, we actually get 4 times 63. Now, 63, is that as far as we can take that? Well, the answer is no. Actually, it's not, because if you remember your multiplication tables, 4 times 63, let's see, 63, I think, yes, that's 7 times 9. So we can write that as 4 times 9 times 7, all under the radical. Now, we have two numbers here, the 4 and the 9, that are perfect squares, and we have a 7 that is definitely not a perfect square. Let's combine the two perfect squares. I like this particular method a little bit better. 4 times 9 is 36 times 7. All right? So what's the square root of 36? And then we have the square root of 7. Square root of 36, well, that's just 6 times the square root of 7. So 252, the square root of 252 can be simplified down to 6 times the square root of 7 if we're careful about how we factor it. Okay? That's what they're asking for with property 1. They want you to pull everything that can be used, every factor that can be used with that radical out of it, and leave behind what can't be used under that radical. The 4 and the 9 are perfect squares, and we're taking a square root. We can take those out. They can become a number outside. And you can do it separately. I mean, you can also write it as, 2 times 3 times square root of 7. You could do it that way. Still going to lead you to 6 times the square root of 7. Because if we take the square root of 4, that's 2. If we take the square root of 9, that's 3. And then we still have that square root of 7. Okay? So either way, we're still going to get 6 times the square root of 7. This is one of the forms of simplifying a radical. Now, let's go to 4a. Because 4a is asking us to take the root index and make sure it's as low as possible. And it gives us the 6th root of 4. The 6th root of 4. Now, at first glance, it doesn't look like anything we can do until we remember that 4 actually can be reduced down a little bit, and we can get the 6th root of 2 squared. Now we have an exponent and we have a root index. So we can actually take this and write it as 2. Remember, the exponent is the numerator. The root index is the denominator. We have a fraction that can be reduced. 2 over 6 can be reduced down to 1/3, which means the cube root of 2 is actually the reduced form of 6, the 6th root of 4. Now, there is no easy cube root of 2, so that's as far as you can go. You can't simplify it any farther. Now, there is a number that times itself will give you 3, but it's a long decimal number, and keep in mind that it may not even be one of those numbers that stops. Remember that we do have decimals that are ever repeating, so keep that in mind. Anytime you run into something like this, leave it at the radical and the number underneath it. 6 times the square root of 7 is reduced because you can't go below that. Cube root of 2 is reduced because you can't go below that. Now, let's look at number 5, 5a. We're going to look at what property 3. Now, property 3, let's scroll back up because I believe that, that is the one where there's no radicals in the denominator. Okay, I'll tell you what, I'm not going to do A. I'm going to do G. I think that I did an example that shows what you do in the case of A. But what happens if you have something like G, where you have a fraction, a 4, and you have a square root of 7 plus a square root of 3. Now, the first thing you might be thinking is, can I combine the square root of 7 and the square root of 3? And the answer is no, you can't, because it's addition and subtraction. If it was multiplication, you could, but addition and subtraction, no, you can't do that. So we have to figure out some way of getting those out of the denominator. Now, in Algebra 1, you should have run across what we call conjugates. Conjugate, let's put this, square root of 3. Conjugate is something you multiply by a binomial, or an expression that has two terms in it, that gives you a perfect square. For instance, if I multiply square root of 7 minus the square root of 3, that would be a conjugate. But I have to put it in the numerator too, because remember, I can only do this if I'm multiplying it by 1. And the square root of 7 minus the square root of 3 over the square root of 7 minus the square root of 3 equals 1. This is a trick we can use. Now that leaves me with my numerator. Kind of cumbersome, but that's all right. But let's FOIL these two out here, okay? I'm going to write it down here. If I take square root of 7 plus square root of 3 and FOIL that with square root of 7 minus square root of 3, well, remember that FOIL is first. Square root of 7 times square root of 7 is, well, 7. Square root of 7 times the negative square root of 3 gives you a minus square root of 7 times square root of 3. Okay, that's your outer. First outer, then inner. That's positive square root of 7 times square root of 3. And then you have your last. Square root of 3 times the square root of 3, or actually the square root of 3 times the negative square root of 3 would be subtracting a 3. You note that you're subtracting square root of 7 times square root of 3, and you're adding the square root of 7 times square root of 3. Those two cancel out, and you're left with 7 minus 3, which actually equals 4. So this becomes a 4, which actually gives you, in the end, let's get rid of that. Let me write it down here. Gives you, the 4's will then cancel out, and you're left with the square root of 7 minus the square root of 3. Let me write that 7 a little more clearly. So the answer is actually the square root of 7 minus the square root of 3. Now, this is essentially all of the things you're going to have to do in this lesson. Unfortunately, it wasn't as short a video as I would have liked, but I'm trying this. I will work on getting better as we go along. I hope this video does help. Good luck on this. I only want you to go to number 7. Don't worry about doing the challenge problems unless you really want the extra work. If you want to practice and do the extra work, you go right ahead. It'll be good for you, but I'm not going to require it. I wish you all the best, and I hope this video does help. Take care. Bye.